So in this video, we're going to consider Shannon's crowning result that he published in 1948, the so-called noisy channel coding theorem. What this theorem states is that it is possible to communicate through a digital channel that introduces errors so that the error correcting code can correct all the errors, not just the single bit errors, but all of them. And we'll be very interested in the conditions under which you can do that. This is going to lead us to define the capacity of a channel, which is the magic number that summarizes the error behavior of the channel. And once we understand that result, this will lead us to understand why is everything digital. There's no longer really much left anymore that's analog, and we'll see why that is in just a second. So let's review the digital communication model. We have a digital source, and it goes through the compression stage, and we then go through the channel coder, which introduces the error correcting codes. It gets sent through a channel that has a probability PE of flipping a bit. And we've already seen there are error correcting codes such that the decoder can correct those errors as long as there aren't too many of them. We worried about a single bit error correcting code. And once you correct those errors, you have now the same, you can get out the bits that you were sent, which allows you to reconstruct the signal, and you're very happy. However, this only mitigates the channel errors. If there happens to be 2 bits in error instead of 1, there's nothing that Hamming code we talked about can do. It will totally foul up. So we can reduce the errors with those single bit error correcting schemes, but we can't make them go to 0. Well, Shannon asked, can we remove all channel induced errors? Is there such a powerful error correcting code that we can use it and not worry about any kind of errors that the channel may be introducing? And clearly the answer was yes, you can. But let's see what the statement of the result is. So the noisy channel coding theorem says let E be the efficiency of the code. So if you recall, we have an NK code, where N is the length of the code word that's used to represent K bits, K data bits. If that efficiency is less than the capacity, C, of a channel, then there is an error correcting code that has the probability that as the length of the code word goes to infinity, the probability that you can decode without that the decoding will incur an error. We get this straight. So if the decoding will incur an error is 0. In other words, you can get the data through without error. And that's so long as the efficiency of the code is less than the capacity. And I'll show you in the next slide what the capacity is. I want to point out some things though first, and that is this limit here means that the code word length is going to infinity. Since we're keeping the efficiency a constant, that means there are more and more data bits are being used in the error correcting code. So this code word is going to get very, very long. But if you do that, despite what we may have been seeing, there exists an error correcting code out there such that you can make the probability of an error occurring in the recovered data block 0. He then proved a result which makes this capacity a very special number. If the code efficiency is greater than C, then all error correcting codes will always incur decoding errors. In other words, again, as the block length goes to infinity, the probability that there's an error anywhere in the data block is going to be 1. So you better have a code, use a code whose efficiency is less than the capacity. If you try to use one that's a little bit weaker, doesn't add as much error correction, you will never be able to correct the errors. So what is the capacity? So for our little channel, the digital channel we've been talking about, the capacity is given by this formula. And if you seem to say that looks a little bit familiar, it does look like it's the entropy formula applied to PE and 1 minus PE. in fact, 1 minus an entropy formula involving those quantities. So here's a plot of capacity. So let's focus on the extremes here first. Let's look at PE equal to 0. The capacity is 1. And since E of the efficiency of the code has to be less than C, not N, has to be less than C, that means that we can have efficiency of 1 when PE is 0. Well, efficiency of 1 means there is no coding, that all that's in a code word are data bits, and certainly if there are no errors in the channel, we'll just send the data through. What's your problem? On the other hand, the other extreme, when PE is a half, that means the channel is randomly flipping the bits, and it's total chaos basically coming out of the channel, and there is no error correcting code because you cannot send things through. The efficiency has to be 0, and why bother? So at some intermediate value of PE, you cannot use a code that's greater than this capacity if you have any hope of getting the message through without error. If you try to use something that has a greater efficiency, greater than capacity, you're going to have errors. You just can't do it. What's interesting about this plot is that you can plot it for PE greater than a half. There's no reason you can't, and kind of falls out of the math that in the case where PE is 1, that means the channel is flipping reliably every bit, changing a 0 to a 1, changing a 1 to a 0, and the efficiency is 1, you might as well just send all the data because all the channel decoder has to do is just flip the bits back. So automatically that result is taken into account, so a really bad PE turns out to be equivalent to a really good one. So Shannon's result is symmetric in that way. So let's talk about a few issues with the noisy channel coding theorem, which are pretty important. And the first is this phrase that keeps coming up: there exists an error correcting code. Well, to this day we don't know what that code is. There are two candidates out there that are being studied today, and they come very close to the so-called capacity limit, but no one's proven that they can satisfy the noisy channel coding theorem. Shannon's proof of the noisy channel coding theorem is fine. There's nothing wrong with it. It's just that it is not what we call constructive. It doesn't give you an example. The proof of it did not use an example code. It was proven a different way. So we still don't know what the code is. But there's a more practical problem, which has to do with this limit as n goes to infinity. So this means the code word length has to go to infinity, which means you're also taking in more and more data bits and encoding them all at once, sending them through the channel, and then decoding them. So this incurs what we call a coding delay, and you also have to wait for all the data to come in before you can run your channel code. Well, that isn't very nice, and the capacity that obeys this result is sometimes called the C infinity capacity, which means you need an infinite length code word. And what we'd like to talk about is what is the capacity for a finite length code word. It's certainly, if it exists, it's going to be less than C infinity capacity, but we don't even know if there are a noisy channel coding theorem for such a thing. It's not clear that you can correct all codes with a finite length block, but people are certainly working on that so we can have practical codes. Well, Shannon also derived a capacity when we take into account the fact that underneath our digital channel there's really an analog channel. So we always abstracted the analog channel, it's adding noise, the signal set choice and everything, and just call it a digital channel. But if you go back down and you talk about a white noise channel having a bandwidth of W and having to figure out what the signal sets are, then Shannon's result says yes. If the data rate of the source is less than the capacity, then you can have what we call reliable communication. No errors will occur if you have the right error correcting code. So if the rate is less than the capacity, you can send information through a channel without error somehow. And here's the formula for capacity. So W is the bandwidth of the channel in hertz. The signal-to-noise ratio is the signal-to-noise ratio in the channel. And this result is in BPS because of the law of base 2. And just as before, if you try to send at a data rate greater than capacity, it's impossible to have reliable communication. You're always going to incur error. So nowadays, when you try to design a digital communication system, one of the things you do is calculate the capacity to make sure that the data rates you're trying to send through that channel satisfy this bound. If they don't, you're going to have errors. If you use a data rate less than capacity, then there's hope that there is a signal set and error correcting code to do the job. But like I said, we don't know what they are yet. But no one tries to send at a data rate greater than capacity because there's no hope. So I want to go through our little example that we've done before. And if you recall, we were trying to send an analog signal through a channel here, and the analog signal had a bandwidth of 4 kilohertz. So we're going to send it through an A to D converter and sample it. Now, thing to note is that the analog signal incurred a quantization error. And once we run it through that A to D converter and you sample it with a finite number of bits, here 4, there is an unrecoverable error. We cannot get the original signal back. So what I want to ask is, can we mitigate the communication errors? Can we get rid of them so that we only have the quantization error of the A to D converter? So for this example, the sampling rate is, of course, 8 kilohertz, twice the bandwidth of the signal, and I'm using a number of bits of 4 in my A to D converter in this example. So we have a data rate of 32 kilobits. So we want to know for what channels is the capacity greater than 32 kilobits. And I have here a color plot that shows how that works. So the large area in color here, all I'm doing is plotting the capacity as a function of SNR and channel bandwidth in hertz. So, and the 32 kilobit plane is shown, and so this boundary here shows us which channels can support a data rate of 32 kilobits so that you can get the information through without error, at least in theory. So we can see that as the bandwidth approaches about 4 kilohertz, you're going to need a very high quality channel because the SNR you're going to need is very, very high. Furthermore, if the SNR gets low, it turns out the bandwidth is going up and up and up, and that's kind of standard. So if you're anywhere in this region, it's impossible. You're in big trouble. So you want to be in the region that's inside this boundary. You want to be in there somewhere in order to communicate this signal, have a hope whether it's sending this signal through without error. I want to compare this result with the plot we had for the signal-to-noise ratio. So if you remember this plot, I was comparing analog communication, which is the resulting message signal-to-noise ratio was given by that line as a function of the channel signal-to-noise ratio for 4 bits and 8 bits. And I'm only going to do the 4-bit example again. So turning things around a little bit, we want to know what signal-to-noise ratio will work, And the data rate, of course, is the sampling rate times the number of bits in the ADD converter, and when you work that all out, you get this. Well, for the case that we were worrying about an 8 kilohertz wide channel, which so that you could use the same bandwidth as the analog signal requires. Modulated analog communication required an 8 kilohertz bandwidth channel. Suppose you made the digital channel live with 8 kilohertz. What signal noise ratio are you going to need? Well, you can do that in this calculation. WC and FS are the same quantity, so you just get 2 to the B minus 1. So the answer is 15, which in dB turns out to be about 11. So what results is I can send my information through my channel, my channel somehow. If the SNR is bigger than this number, then I will incur no communication error. Only thing I'm left with is the quantization error. That's this plateau. But once I drop below this magic number, it turns out the signal-to-noise ratio goes to basically 0. And I can't get anything through. And this is the capacity wall, it's called. Once you transmit it, have enough signal to ratio so that you're above some magic threshold, things are fine. Well, if you fall below it, things are not very good at all. You're going to be in big trouble. And as you can see from this plot, you're better off not using any channel coding at all. And this is what happens when you use BPSK and don't do any channel coding. In that situation, in this regime, you're better off not trying to do channel coding at all, but you're always incurring error. And that's the sad result. But there is a region over which you can get through and live only with the quantization error. Very, very nice. So, why is everything digital? So, sources can be compressed, first of all. And that's either lossy or lossless, depending on whichever you're doing. If it's lossy, and you could consider running an analog signal through an A to D converter as being a lossy compression scheme. It's representing the signal with bits, but you cannot recover it. Same thing as compressing music with an MP3 compressor. That's lossy compression. Be that as it may, you can convert basically any source into a sequence of letters, which can be compressed in the source coder somehow. We can find a error correcting code that's very good as long as it obeys the noisy channel coding theorem. We know we can actually decode without error. So that means once you are willing to incur the error in digitizing analog signals, converting it to bits, turns out that means now digitized signals and inherently digital signals like text can now be transmitted over a common communication scheme without error. And that is really interesting. So once you have bits, you got a chance. You can send the bits through a channel with no error. There is no similar result for analog channels. Once you have error, or the noise introduced in an analog channel, you have to live with the errors if you stay analog. But if you go digital, or if you have a digital source, you can correct those errors that the channel will introduce if the situation is correct. In other words, if the data rate is less than the capacity. Well, this ability to send any kind of signal once it's bits, that leads directly to computer networks, where computer networks now can carry any kind of signal, be it SMS, be it your voice, be it an image, be it a video. We all can put all those different kind of messages into a common communication scheme, and the reason for that is Shannon's noisy channel coding theorem.